Hi, this is Dr. Swope. I'm making this video so that you can learn a bit of physics. And don't forget, this slide is showing us a picture of a series circuit. You can see all the resistors are one after another one, and there is only one path for the electrons to flow through the circuit. What we'd like to do is come up with an equivalent resistance that sums up all of resistors 1, 2, and 3. For a series circuit, you can see from equation 4 that it's actually pretty straightforward. Just add up all 3 of the resistors, or 4 or 2 or however many there might be in that series circuit. Okay, well, if you have time, see if you can copy down this diagram. We're going to be coming back to a diagram very similar to this one, and we're going to have some resistor values. Notice that we've also put the current flow with a small letter I. It's a little bit better looking at little I than the big I, so that's what they use. And there is one current that flows through a series circuit. It's always the same. This frame shows a parallel circuit. Well, I guess it must get its name because all the elements are in parallel with each other. This time notice that there is a subscript next to the little current sign. So you have the total current that leaves the battery and comes back to the battery. And then it branches down through all of the resistors individually. So you get I1, I2, and I3. Okay, well, I1 and I2 and I3 do not necessarily equal each other. So they're a special case when they would equal each other when the resistors would be the same value as each other. Okay, the sum of I1 and I2 and I3 all have to equal IT. So the total current branches out and then it comes back again. So I1 plus I2 plus I3, they all together equal the total current. Well, you can see there that there's a kind of a fancy way of combining the resistors. So then you have to do the sum of the inverses. It's equal to the inverse of the total resistance. Now you don't always need to kind of do a major calculation to calculate the equivalent or the total resistance in a parallel circuit. Sometimes if the resistors are all the same value, then you can simply take the resistor value and divide by the number of resistors to come up with the equivalent resistor. Right now this example shows 3 resistors in parallel. Okay, and you can maybe show for yourself if there were 2 or if there were 4. Right? You want to get real ambitious, maybe you can try 10. And 10 resistors in parallel, go ahead and show yourself that that would turn out to be the resistance divided by 10. Power is measured in watts, and the way that you can come up with power in electronics is using the voltage times the current. Well, you can do this for the total circuit. If you know the total current and the battery voltage, you can do it for an individual element. If you know the voltage that is dropped across that element and the amount of current going through that element. Right, as you can see in equations 2 and 3, there's also a couple other forms for the power. Those are useful, let's say, if you don't want to calculate the voltage or the current, and you still would like to find out what the power is. Okay, now you can see, kind of stepping through there, looking at equation 6, that the units, if you multiply voltage times current, do indeed come up with the units for power, watts. Okay, we're back to the series circuit. Now, if you haven't already drawn this, it might be a good opportunity for you to draw it now. We're going to give values to R1, R2, and R3. Okay, if you can't read that, it's 10, 20, and 30 ohms. Now, in series, we're just adding up the resistances, come up with total resistance. And we're going to be doing this over and over. So we come up with the total resistance, sometimes called the equivalent resistance. We can calculate the current then by dividing the voltage supplied by the battery divided by the equivalent or the total resistance. Once you've worked out the current flowing through the series circuit, remember it's the same current going through each element. Then you can work out the voltage dropped across each element. Notice that if the resistances are different values to each other, then the amount of voltage dropped will be different as well. Okay, well, if we've done it correctly, then all the numbers should add up to the total voltage that the battery has. Okay, well, all the money is in this one now, so power is where it's happening. Remember, we worked out that we could figure out the power if we multiplied the voltage times the current. Notice that when we work out the power dissipated by resistor 1, then we use the voltage that is dropped across resistor 1. You can notice also that in these equations, there's only one current. So probably the biggest thing to remember then for a series circuit is the current stays the same throughout the whole circuit. Right. This is a very busy sketch, as you can see. Now, if you haven't written down this parallel circuit, this would be a good time to do it. As you can see, we've given each of the resistors some values. Now, I've rewritten the parallel resistance formula. Once you've come up with the total resistance, then you can work out the total current going through that circuit. Okay, now that total current again leaves the voltage, leaves the battery, comes back to the battery. Notice also that the total resistance is less than the least resistance. Okay, well, you probably underestimated the utility of that Ohm's law. You can see here that we were able to use Ohm's law then to work out the individual currents in each branch of the parallel circuit. This time there is only one voltage. It's probably one of the most difficult things for students to get their heads around. The voltage is the same. So we've got one voltage. It's going to be equal to the same voltage that the battery has in this particular case. Okay, so we take that voltage, divide by the individual resistances, and we're able to come up with a total, we're able to come up with the current going through each element. If we add all those up, we come up with the total current in that system. Okay, yep, so there is a little bit of rounding involved. So yes, indeed, we're not exactly the way it was before. Now we've calculated the power here for element 1. You can go ahead and do it for elements 2 and 3 if you'd like. We can also calculate the total power. Well, probably a few of you have been sitting back waiting to hear about combination circuits, and so not to disappoint you. Now you might need to sketch this one up just to make it a little bit less confusing. We've listed the resistance values separately. When you have a combination circuit, what that means is you have both series and parallel portions of the circuit. Now we've called the total resistance for the parallel portion R23. We've calculated that using the parallel rule. And then we treat that as a series element to come up with the total resistance for the circuit. Now the actual circuit analysis for a combination circuit is a lot more fun, mainly because you know, it's a bit like working out a crossword puzzle or a Sudoku. So you can kind of come up with the total current as you did before. You can see that one in equation 1. Once you've done that, then you can come up with the voltages across each element. Notice in number 2 we've come up with the voltage drop across the parallel portion of the circuit. We call it voltage 2,3. Okay, then in equation 3 we're using voltage 2,3. Scratch that. In number 4 we're using voltage 2,3 to come up with the individual currents. Now what we've done in number 3 is to show you an alternative way to come up with the voltage 2,3. And once again we're back to the money page, because people that work out power tend to make more money, and also this is where you're going to be spending your money, and this is where the energy gets expended. Now if you're going to be designing a circuit, you need to work out how much energy is being expended so that you can design your battery. You can work out how much heat is going to be dissipated so you can get rid of the heat, so you don't burn up the circuit board that you're making. Okay, well, now you could have worked out the power in just about any formula that you liked, and just to shake it up a little bit, we've used I squared R for the individual powers. Okay, now notice again, we've done a bit of rounding, so all the numbers aren't exactly equaling each other. And don't forget, and don't forget, and don't forget,